So in this lecture, we are going to discuss about the timer and the count delay and how to solve the problems which are related with the timers and the count delay. Suppose we have a problem which is saying that write a program to generate a delay of 0.4 second if the crystal frequency is 5 megahertz. Again, since the crystal frequency is going to give you the time period of 1t state, so we have to calculate what is the time period, what is the value of t state. So for obtaining the value of the t state, it is necessary that to obtain the value with the frequency, but since the crystal frequency is given, we have to find out the operating frequency. And I have already told you that operating frequency is half of the crystal frequency. So how it works? So in 8085, the operating frequency is always half of the crystal frequency. So the operating frequency will be 5/2, that is 2.5 megahertz. And time for 1t state will be 1 upon, because we know the formula, f is equal to 1 upon t or t is equal to 1 upon f. So t will be equal to 1 upon f, that is 1 upon 2.5 megahertz. And that is coming around 0.4 microsecond. So in this problem, we have to generate a delay of 0.4 second. And the frequency, operating frequency is 2.5 megahertz. So time for 1t state become 0.54 microsecond. So it means we have to calculate that how many t state, if we write a program, and the program should be such that it should consume a number of t states so that it will be able to create a delay of 0.4 seconds. So we know the time for the 1t state, and the total delay we know that is 0.4 microsecond. And the time for the 1t state is 0.4 microsecond. So with that, we are able to find out the number of t state required. So number of t state required will be the total required time, which is required for the delay, that is 0.4 second, upon the time for the 1t state. So for obtaining a delay of 0.4 second with time period of 1t state 0.4 microsecond, how many t states will be required? And that is obtained, that is equal to 1 into 10 to the power 6. It means we have to write a program which will consume 1 into 10 to the power 6 t states. So I have written a program, and that program will be using, of course, if we need, as you have seen that there are many ways by which delay can be provided. First of all, the delay can be provided by using NOP instruction, but that delay is very less because NOP instruction used to take only 4 t states. So the delay which can be provided will be 4 into its time period. Then we have seen that delay can be provided by loading a count value into an 8-bit register, but you have seen that the delay which we are getting in the with the 8-bit count value, it is coming around microseconds. Then we have seen that the delay can be provided by using register pair, with which we are able to create a delay in milliseconds. So here, what we are going to do, we are using a BC pair register, means 16-bit count value into a BC pair register by the first instruction, that is LXIB count. Now we don't know the value of the count. So the count value will be estimated later on. So first of all, we are going to load the count value into the B register. It means 16-bit count is loaded into the BC pair register, and it used to take 10 t states. Why it is taking 10 t state? 4 t state will be consumed in opcode fetch, in fetching the opcode of LXIB, and the count value is 16-bit, so it will be memory read operation, and again will be a memory read operation to 4 plus 3 plus 3. So it is total accounting to the 10 t states. Then we have second instruction I have used, that is DCXB, which is going to decrement the content of the BC pair register by 1. Now, there is a difference between DCXB and DCRB. Whenever we write DCXB, it means we are considering B as a BC pair. Whenever we are writing DCRB, it means we are considering B register as a 8-bit register. But whenever we write DCXB, it means we want BC pair. So DCXB will be decrementing the content of BC pair register by 1. How the BC pair register content will be decremented? In BC pair, B register contains the higher order number and C register contains the lower order number. So first of all, lower order number will be decremented by 1. And the time when C register content becomes 0, then it will start the decrementing the B register content. So it means a long time will be elapsed while using the 16-bit count. So then we have now this DCXB will be taking 60 states. Then I have used instruction move AC, which is simply copying the content of C register into accumulator. And then it will be taking 40 state because it is single byte instruction. Then I have used ORAB, which is going to logically OR the content of B and C. Again, it will be taking 40 state and jump on no 0 back. If it is not 0, it is going to repeat. So we have created a loop which will depend that how many times it will work. It will depend upon the count value. So the total, let us calculate the total time elapsed by using this particular program. And then we are able to calculate what will be the value of the count. So in this particular case, the total time required to execute the program will be equal to the time elapsed in evaluating the instructions, which is outside the loop as well as inside the loop. So it means the total time will be T loop and T outside loop. So in T outside loop, we have this 10T state. So 10 has been included here, plus whatever is the count value, count minus 1 multiplied by 6 plus 4 plus 4 plus 10. That is equal to 24. Plus, when the count value will become 0, it will take the time period T state as 6 plus 4 plus 4 plus 7. It is equal to 21. And this total T number of T states consumed in executing this program multiplied by the time period of 1 T state. It means this within bracket, whatever I am representing, it is the total number of T state which will be for this particular program multiplied by the time period of 1 T state. So total time required to execute the program. Now we want in this problem, we want a delay of 0.4 second. It means total time required to execute the program is, if I evaluate it as 0.4 second, and that will be equal to 10 plus count minus 1 into 24 plus 21 into 0.4 microsecond. So if we evaluate this bracket expression, so 21 and 10, it will become 31 plus count minus 1 into 24 into 0.4 microsecond. So it means if we take this time, this function value, this expression left hand side, so what will happen? It will become 0.4 second upon 0.4 microsecond, that is equal to 1 into 10 to the power 6. It means the count value will be equal to what? 1 plus 1 into 10 to the power 6. If we put this 31 on the right hand side, so minus 31 divided by this 24, and then count minus 1, so it will become plus 1 here. So that whenever we are going to evaluate 1 into 10 to the power 6 minus 31 divided by 24 plus 1, that is coming around 41,666 decimal. And when we convert this decimal value into hexadecimal, then we will be getting A2, C2. This is the approximate value, because whatever we are calculating, it will be coming in the decimal, but we have taken the approximate value, that is 41666, which is later on converted into hexadecimal number. So it will become A2C2. 41666 decimal number is equal to A2C2. How to find out how to convert the decimal number into hexadecimal number? So by dividing this decimal number by 16, so whenever you are dividing this number by 16, you will be able to get A2C2. So this will be the program, and with this program, since you want 4.4 second delay, so you will be getting count value as A2. Now, if anyhow we want this delay to be lesser or more, then in that case, the count value you will be getting will be different. If this count, if this 0.4 second in place of, if you require 0.04 second, or if you require 0.8 second, then in that case, the count value will be different. So depending upon the delay which we are in requirement, we will be getting different count value. So for this kind of problem, it is not only to calculate the count value, but to write the program as well as to calculate the count value, then only this problem is said to be completely solved. So to generate a delay, we can use in this particular program, we have used the BC pair register, 16-bit count into the pair register. And then we are going to decrement it one by one, calculating the total number of T state multiplied by the time for one T state. And that is equal to the total delay which is required, that is 0.4 second. If 0.4 second is different, we will, instead of 0.4 second, we will write it different. And so at that time, count value will be different. So in this way, this kind of problem can be solved to find out the value of the count. Write the program and to find out the value of the count. So this is how this is going to work. Now the next one is the hexadecimal counter. Now, hexadecimal counter, the problem is write a program to count continuously from FF to 00 with clock period 0.5 microsecond. It means clock period is equal to 0.5 microsecond. It means time period of one T state is 0.5 microsecond. It means microprocessor in 0.5 microsecond used to do one subdivision of the operation. Now the problem says that use register C to delay 1 millisecond. Now here we are in requirement of only 1 millisecond between each count and display the number at the output port. So let us first understand the problem itself. Problem says that you have to display a hexadecimal number on the LED display screen, which is connected at the output port, and at a particular time that LED display should display FF, and after 1 millisecond delay, it should display FE. After 1 millisecond delay, it will display FD. After 1 millisecond delay, it should display FC. After 1 millisecond delay, it should display FB. After 1 millisecond delay, FA. Meaning thereby, whatever number we are displaying at the LED display should remain for 1 millisecond. And after 1 millisecond, it should change to the different second value. So this says that you have to count continuously from FF to 00. So pehle value that will be FF, then FE, then FD, then FC, then FB, then FA, then F0, then F9, then F8, F7, F6, F5, F4, and each value will be decremented after 1 millisecond. So for that particular purpose, we have to write the program. 1 millisecond delay के लिए वो displayed रहा है, और time will come when it will from FF it will display last value will be 00. It means you have to display 255 numbers because the the maximum value is FF and the smallest value is 0, 0. And in between FF and 0, 0, there are 253 more numbers. And in totality, there are 255 numbers from FF to 0, 0. So let us first discuss the flow chart, and then we will discuss the program, and then we will find out the count value. Now, as the flow chart says, first of all, we will be using a single 8-bit register to load the counter. We will decrement the counter. Then, now this counter B will be used to display the number, and delay counter will be used in register C to make a delay program. So first of all, we will initialize register B, which will be used to display the value. Register C will be used to load with the delay count value. And this delay count value, whenever it is being initialized, we will decrement the delay counter and check whether the counter has become 0 or not. When it becomes 0, then we will display the output. And then when we display the output, then we will go to the next count. And next count is, we are going to decrement the counter. We again load the C register with the delay count value and again decrement, and in this way, this program will work. Meaning thereby, first of all, we have to display FF. So it means your B register should contain FF. Then it should be decremented and it should become FE. Then it should be decremented and it should become FD, and so on. And similarly, since we require a delay also in between the display of FF and FE, we require a delay in between the display of FE and FD. Again, we require a delay of 1 millisecond in between FD and FC, and so on. So we have loaded first the register counter B with 0, 0. Whenever register counter B is loaded with 0, 0, B will be placed with 0, 0. And then I have used instruction decrement B. So whenever B is having 0, 0 and it is decremented by B, automatically the B register will contain FF. How? You know how whenever we are going to decrement 1 from 0, 0, we will be getting FF. That's why I have asked you all to write a sequence of the number from 0, 0 to last one. Whenever, now you see, the simple explanation of whenever we are having 0, 0 in a register and we are decrementing it B, how it will become FF. It is very much clear. When you have FF in a register and if you want to add 0, 1, what will be the result? The result will be 0, 0. It means if you are adding 0, 1 in FF register, in FF, you are getting the result as 0, 0. It means whenever you are subtracting 1, 0, 1 from 0, 0, you will be getting FF. It is very much similar to that if you add 1 in 1, you are getting 2. So if you are subtracting 1 from 2, you will be getting 1. It is very much similar to that. Hope you understand. So whenever B is loaded with 0, 0 and you are doing decrement of B, what B will have? B will have FF. Then we have to load we have to use a register C, which will have delay count value. I don't know. We don't know what will be the count value. That will be calculated later on. So we have put a count value into the C register. Now C register will be having that count value, which will be creating a delay. So how it is creating a delay? Suppose we have loaded the count value in a C register and we are decrementing. Suppose the count value is 7. So whenever we are decrementing, it will become 6. And jump on no zero delay. Jump on no zero delay. Till this C value is not 0, it will go and loop in it will be in this particular loop. It will remain in this particular loop. And then what I have done, we have copied the value of B into A, and I have sent this content of A to the B port 1. Now, what is the content of B right now? The content of B is FF. It will be copied in accumulator, and this accumulator content, that is FF, is ported with the output instruction. It receives, it is being received at the port 1. And at what is at port 1? At port 1, we have a LED segment display. So it will be displaying FF. And then we are saying jump next. So it will jump next, it will come over here. So whenever it will come over here, it is again going to decrement B. Now, previous value of B is FF. Now it will be decremented by 1. So it will become FE. Again, the C will be loaded with the count value. And again, we will be in a loop so that it is going to create a 1 millisecond delay. And when it is created, 1 millisecond is created, then what will happen? The content of B will be loaded in A, and then it will be sent to the output port. It means before displaying FE, we have consumed 1 millisecond by putting a count value into C and putting this loop into the existence and executing it. And then it is being displayed at the output port. Again, it is going to jump next. The content of B register will become FD, and then C is again loaded with the count value, and it is decremented, and it will be consuming some time in executing this loop, and then FD will be copied into accumulator, and then it is being displayed at the LED display at port number 1. And in this way, this process will go on. Now here, for the simplicity, jump on no zero delay, I have taken only 10 T states, and this /7 T state has been ignored. Assuming that it is 10, because it is going to give you the clear idea, more easy for the calculation purpose. So how much time it is elapsed in the loop? How much time it is going to elapse in the loop? Now you see, 4 plus 10, 14 T state into the 5.5 is the time period. So 0.5 into 10 to the power minus 6 microsecond. I'm talking about this loop only these two instructions. So 4 plus 10 multiplied by the clock period means 0.5 microsecond into the count value. Because this loop will happen how many times? Up to the count value. If the count value is 5, it will be multiplied by 5, because 5 times this loop will work. So for simplicity, I have done. Otherwise, what you have to do, I have to calculate it with count minus 1 plus 4 into 7, that is 11. So just for the simplification of the calculation, I have done this. So T loop is equal to 7 into 10 to the power minus 6 into count. And now the delay outside the loop will be, what are the outside instructions? 4 plus 7 plus 4 plus 10 plus 10 is equal to 35 T states. And 35 T state will consume how much time? 35 into 0.5 into 10 to the power 6, that is 17.5 microseconds. So the total delay which will be used will be T delay is equal to T output, means outside the loop, that is 17.5 microsecond, plus 7 into 10, loop का timing क्या है? 7 into 10 to the power 6 into count. Now the total delay which is required is 1 millisecond. So we have put this TD value as 1 millisecond equal to 17.5 into 10 to the power minus 6 plus 7 into 10 to the power minus 6 into count. So what we'll do, this 1 millisecond is equal to 1 into 10 to the power minus 3. Then we will put this value in the left hand side. So 1 into 10 to the power minus 3 minus 17.5 into 10 to the power minus 6 divided by 7 into 10 to the power minus 6. That will be going to give you the count. And whenever we are going to calculate 1 into 10 to the power minus 3 minus 17.5 into 10 to the power minus 6 upon 7 into 10 to the power minus 6, we are able to get the count value. And the count value which we will be getting, that will be equal to 140. Approximately, roughly, it is coming around 140. And this 140 is a decimal number. So converting this decimal number into hexadecimal number, So we are getting 8C. So means this count value should be 8C. And if this count value is 8C, this is going to create a delay of 1 millisecond. So it means, first of all, FF will be displayed. And then after 1 millisecond of delay, FE will be displayed. Then after 1 millisecond delay, FD will be displayed, and so on. So in this way, this hexadecimal counter will be working all together. So if you want to really go through the calculations, this count value, you can do it from here. If we elaborate it as, so count will be equal to 1 millisecond will be 1 into 10 to the power minus 3, that is 1 millisecond. Minus 17.5 into minus 17.5 into 10 to the power minus 6 within bracket, and that is divided by 7 into 10 to the power minus 6, and that will be equal to this calculation we have to do. 1 into 10 to the power minus 3 minus 17.5 into 10 to the power minus 6 upon 7 into 10 to the power minus 6, that will be equal to count value. And that count value is roughly coming 140, and that is approx, because it might be coming in that will be coming approximately, because it will be coming in decimal number. So whenever you are calculating, it will be roundabout, it is coming as 140 approximately. And this 140 is the decimal value, and we have to convert this decimal value into the hexadecimal value to find out. So in this way, this is going to work. For simplicity in the calculation, I have ignored this 10/7, because if we consider this 10/7, if we ignore, if you're not taking to, then it will become, if I consider this one, then it will be count minus 1 plus 4 into 7, 11. And this will be taken out. And then it is multiplied by 0.5 minutes. So for simplicity, we have done that. We have ignored 7, considered that in the last lap also, when the loop is going to satisfy, it again takes 10, because three t states से बहुत कोई फर्क नहीं पड़ता है. So that is why I have not taken into the consideration. So this is all about